Hello everyone, this is Aditya, and today I am starting a lecture series on a special theory of relativity, and this is the lecture 1. And in today's lecture, we are going to discuss inertial and non-inertial frame of reference, Galilean transformation, and non-variance of Newton's laws of motion in Galilean transformation. So let's start the lecture. But for that, please do like, share, subscribe, and please support this video. Now let's start. And yeah, when I will be done with this series, I will compile all the lectures in one video to make it like a kind of one shot, and then I will upload it again. So if you find it more easy to watch the complete lecture in one go, like in a one shot, you can follow that series after I complete this. I mean that video. And if you are more comfortable in watching lecture wise videos, then you can continue with this. Okay, so now let's start the lecture, right? Okay, so first of all, let's start with inertial and non inertial frame of reference. Okay, so first of all, before understanding inertial and non-inertial frame of reference, we need to understand what is the need of a special theory of relativity, right? So when Newton proposed his theory on motion, he stated certain things like that time is absolute, space and time are different things. Basically, these two are the things, and there are many other points also, but right now, to make you all understand, I am just sticking to these 2 points. Okay, particularly with this one. Newton told that if there is any particle, suppose there is a particle, if it's moving with a velocity v and there is an observer in that frame of reference, then suppose this whole frame is moving at a velocity v and there is another observer over here. Okay, and suppose if he measures a time t0 and this frame, the observer in this frame measures a time t, then the relation between t0 and t is t0 is equal to t. That is, time is invariant of frame of reference, velocity or anything. Newton told this. But then came Einstein and he said, no, that's not true. Time is not absolute. Time is not absolute. Okay? And he also stated space and time are not different. Rather, they belong to a bigger idea called space-time. Space-time. Okay? Right. So time is not absolute. Okay? That is the idea. Now what are the postulates of relativity? A special theory of relativity. The first idea is very clear. Laws of physics are same for all frames of reference. Okay. Second, speed of light is same or constant for all inertial frame of reference, actually for all inertial. A special theory of relativity deals with inertial frames of reference. Okay, so first one was a bit obvious. This thing is the main idea behind relativity. Newton stated that the speed, since he stated a formula F is equal to ma, so if you keep on increasing the I mean, if you keep on giving the force to an object, it will keep on accelerating, and acceleration will be given by F by m. So it means that V is equal to, suppose it was initially at rest, will be equal to AT, right? Now it's possible that AT will somewhere tend towards the speed of light also, or it can go even more than the speed of light. So it means that according to Newton's laws of motion, a particle can achieve infinite speed also. But that's not true. That's not how the universe works. Universe has a speed limit of speed of light. So nature has its own rules, that speed of light is constant, is same for all the initial frame of reference, and it is actually a speed limit. So if any particle is trying to approach the speed of light, then what will happen? To make you all aware of that, a special theory of relativity was proposed by Einstein to explain these phenomena near the speed of light. But in our day-to-day life, where the speeds are very, very less than the speed of light, in normal world which we feel daily, we don't need special theory of relativity, because relativity is somewhat linked with something called as Lorentz factor gamma, which is 1 upon a square root of 1 minus v square by c square. And when velocity is much less than c, then of course v square will be much less than c square. So 1 minus v square by c square will approximately be 1. So gamma will be 1. So in this case, there is no need to think about the relativistic effects of the universe, right? So now let's discuss inertial and non-inertial frame of reference. This was just an intro, right? Okay. So first of all, let's understand what is frame of reference. What is it? To understand this, first of all, you have to understand what is meant by coordinate system. Okay. This is x-axis, this is y-axis, and this is z-axis. Okay, right? So this is a three-dimensional this is three spatial dimension, means space dimensions. Three spatial dimensions. Okay. So you have this coordinate system, right? So if you have to find the position of a particle, then what you will do? Well, you will just need to know its coordinates. Suppose this is 2, this is 3, and this was 4. So 2, 3, 4 will be the position of the particle with respect to the origin. Okay. So to know the distance of the particle from origin, what we do? We need a length scale for it. So we need a coordinate system. Now how we know that this length is 2? What is 2? 2 units. So we need to have a length measuring scale, and at what time is this particle at that position? So we need a time scale also, and of course someone is measuring it, it's obvious. So an observer is required. So if you combine these three things along with the observer, you get something called as frame of reference. Basically a frame, right? Now suppose if this frame, we call it as, suppose, S frame. If you are calling it as S frame, and suppose there is another frame, X dash, Y dash, Z dash, and it is suppose moving at a velocity v. This is S dash frame. as dash frame. Okay, so with respect to this frame is moving at a constant speed or constant velocity. So it's moving at a constant velocity, I should say. And since it's moving at a constant velocity, it means that the acceleration is zero, right? Acceleration is zero. And the frames in which the acceleration is zero and force is zero, we say such frames are inertial frames of reference. And the frames which are accelerated are called as non-inertial frames of reference. Okay, right? Okay, sorry. Yeah, so inertial frame of reference, you know it, right? So it means that inertial frame of reference will follow Newton's first law of motion. First law of motion. What is Newton's first law of motion? Newton's first law of motion is law of inertia. A body moving with a constant velocity will keep on moving at a constant velocity, at that velocity only. And when I speak velocity, it includes direction and rotation, everything in that. Okay, so that is why I stated velocity. Okay, now in case of non-inertial frame of reference, for example, suppose this is a marker. Okay, this is a chalk holder, and if I move it, just observe it. When it is stopping, when my hand is stopping, it is suddenly, and in fact when I am moving it, it goes backwards and it oscillates, right, when I stop. So what is causing it? There's some acceleration there, right? Which means that this is non-inertial frame of reference, right? And suppose if I am doing circular motion, and I keep an object over here, and then I rotate this body, then it will follow a trajectory like this, right? Okay, maybe like this. Okay, whatever be it. Okay, so why is it moving backward or forward, whatever, we have to do that experiment and then we will figure it out. Okay, so it doesn't matter in whatever direction you are going. I should remove it, else you will get confused that direction matters or not. What I mean to say is that when you will rotate, it will go like this or like this. Okay, in outward direction, in a following a curved path. Okay, so why does this happens? There's no other force acting on it. So to explain it, we use the concept of pseudo force. So we say that there is some centrifugal force over here, centrifugal force, and why it is curving? The path is curved because of Coriolis effect, Coriolis force we say. Okay, and these two are the pseudo forces over here. So it means that in non-inertial frame of reference, we can take help of pseudo forces to explain it, right? And in relativity, we don't deal, in special theory of relativity, we don't deal with non-inertial frames of reference. We just deal with we deal with inertial frame of references in relativity. So this was the basic introduction to relativity. Now let's understand Galilean transformation. Okay, so let me erase this first of all. Galilean transformations. Okay. Before starting with Galilean transformations, do you know what is rest and what is motion? Well, if the position of a particle is changing with respect to a point, with respect to a reference point, then we say that it is at motion. and if it is not changing, we say it is at rest. Okay, right? Like for example, with respect to you, this board is at rest, and if I start moving, for your frame of reference, you feel that I am moving, but for me, of course, it is my intelligence that I know I'm moving, right? That is just basic human intelligence, that we can perceive that we are moving. Okay, but suppose if I think that I can't perceive that whether I'm moving or not, and if I observe this board, I will feel that this board is moving backward actually. So motion is relative according to the reference point you are choosing, right? Okay. So now Galilean transformation. Now there are certain rules which we use. This is x-axis, this is y-axis, and this is z-axis. And suppose this is S frame. Okay. Now, suppose this is x dash frame, this is y dash frame, and this is z dash frame, and this is S frame. Okay. Right? Okay. And suppose this frame is moving along x dash axis, right, with a velocity v. Okay, right. And suppose there is a particle which is moving, suppose in vx direction with a velocity vx. Okay, this v and this vx is different. Now there is an observer in this frame, and there is another observer in S frame. Okay, and of course this is at 0, this is at rest. Sorry. So first of all, we have to understand that what is the concept behind this. Okay, we assume, suppose this origin O and this O dash, we assume that x and x dash axis are along same line. What it means is that we choose it like this. They lie along same line. Okay, like this we choose. Okay. Now what is the second point? Time at which O and O dash coincide when they both are like this. O and O dash are like this. There must have been a time when they both would have coincided over here, right? We say that time is called time is equal to 0. That is the starting actually. Okay, and y and y dash axis and z dash axis are always parallel. These 3 points you have to keep in mind while making all the calculations in relativity. Okay, so these 3 are the basic points which you have to remember. Okay, so this y and y dash are always parallel, z and z dash are always parallel, x and x dash are lying along the same line, and when they coincide, the time at which they coincide is set as t is equal to 0. Okay, now let's start. Suppose this particle currently is at rest. Let's assume it is currently at rest. Okay. Now what will be the coordinate of this particle if I assume it with respect to S frame? Okay, let's calculate it. Okay, so this distance from here till here is what? Suppose I name it as x comma y comma z with respect to this frame of reference, and x dash comma y dash comma z dash with respect to S frame, and time is t, and over here let's assume t dash. Okay, right. So what is the relation which we have? Okay, so we are calculating observer is at origin, of course. Observer is at origin. Now let's see. So this distance is x, and what is this distance? This distance is equal to x dash. Okay, now what is this distance? This will be vt with respect to this, right? So from here you can say that we have the relation x dash is equal to x minus vt, x minus vt, and of course there is no change in y and y dash, so we have y dash is equal to y coordinate and z dash is equal to z coordinate. Okay, and this is called as, and yeah, time is absolute over here, so we say it like this. So this is called Galilean transformation. Okay, so this is the calculation of the coordinates of particle P according to the measurements taken by S frame, right? So this is what observer in S dash frame will observe as the coordinates with respect to the calculations of S frame, right? Okay. Now if you know the data of S dash frame and you have to move to this, what you will do? You will just simply say x is equal to x is equal to x dash plus vt, and y is equal to y dash, z is equal to z dash, and t is equal to t dash. And over here we will have vt dash because over here we have to take the time with respect to S frame. Okay, so it means that, and it is called as inverse Galilean transformation. Okay, so this is the first case, the most basic thing in Galilean transformation. Now let's move further in this, and let's talk about when this particle is at motion. So let me erase this, then we'll move forward. Okay, I hope you understood what I mean. This is the coordinate of that particle measured by S dash frame according to the data given by S frame. Okay, this is how you do, and this is just inverse of it, right? Now let me erase this and let's take another further case. Now let's assume that particle was in motion. Okay, x, y, z. Suppose that particle was in motion, x plus dx, y plus dy, z plus dy, t plus dt. Okay, this particle, and this is moving along x-axis with a velocity v. Okay, now what are these coordinates? These coordinates are the position vector of this particle with respect to S frame. Okay, okay. So according to Galilean transformation, whatever will be the x coordinate of that particle measured according to this, it will be given like this. Okay. Now let's find the velocity of this particle. Let's differentiate this. We'll have dx dash divided by dt is equal to d by dt of x minus vt, right? Correct or not? Dt dash, because we are finding with respect to this frame. Dt dash, okay? Now we know t dash is equal to this. Since t dash is equal to t, so it means that dt dash is equal to dt, right? Okay. So from here you can say it as dx by dt dash minus v dt by dt dash. Now dt by dt dash is equal to 1. Okay. Now what is dx by dt? Dx by dt is the velocity of particle with respect to frame S frame, right? So we can say that Vx dash is equal to Vx minus velocity of S dash frame with respect to this frame. Okay, so this is Vx. Similarly, you will apply same maths, same maths for this. So you will have dy dash by dt dash is dy by dt dash, which is dy by dt. Hence, vy dash is equal to vy, and similarly, dz dash. Sorry. Similarly, we can say that vz dash is equal to vz. Okay, and of course, t dash is equal to t will still hold. Now, if that particle is in acceleration, then in that case, just differentiate it again. So you will get d vx dash by dt dash of is equal to d by dt dash of vx minus v. So it is dvx by dt dash minus dv by dt dash. Now since it's moving at a constant speed, constant velocity, so this term will be 0. So we will have dvx by dt dash is equal to dvx by dt. Hence we will have ax dash is equal to ax, and ay dash, similarly ay dash will be equal to ay, and az dash will be equal to az. Again t dash is equal to t. So this is the velocity transformation, this is the acceleration transformation. Now one thing to note over here is that the acceleration in x axis, along x axis, in both the cases is same, are equal, and in y and z also, which means that if this observer observes that a force is applied on this object, suppose F force, since we know F is equal to ma, so if this observer observes a force, suppose like this, F vector is given as ma vector, right? So it is fx vector I cap plus fy j cap plus fz k cap is equal to m ax I cap plus ay j cap plus az k cap, right? So from here you can say fx is equal to max, and we are assuming that the mass is constant. Fy of the particle, Fy is equal to may, and Fz is equal to maz, correct? Right? So when you apply transformation, it should be max dash is equal to f dash x measured from s dash frame, fy dash is equal to may dash, and fz should be equal to maz dash. Now since ax dash is equal to ax, which means that this is equal to fx dash is equal to fx, right? Correct? Just check it once. Ax dash is equal to ax, so it will be max is equal to fx, so f dash x is equal to fx. So the measurement of force will also be constant, right? So it tells that Newton's laws of motion are invariant under Galilean transformation, and it also tells that laws of physics will be same for all inertial frames of reference, right? Now one thing more I need to tell you. Suppose this is a frame x, y and z, and this x dash, y dash and z dash. Now this is at rest, this was at motion with a constant velocity. So be it any frame of reference, any inertial frame of reference, this S dash frame will always remain inertial with respect to all inertial frame of references. Be it whatever be the velocity. Suppose this frame was moving with a velocity u. So with respect to this will always be inertial frame of reference, irrespective of the velocities. So any frame of reference which is inertial with respect to one inertial frame of reference will be inertial frame of reference with respect to all other inertial frames of reference. So let me write this. If one frame of reference is inertial with respect to one inertial frame of reference, then it will be inertial frame of reference with respect to all other inertial frame of reference. Okay, that is what I want to tell, right? And you can prove it also. I proved it even. Of course, if they both are moving at some constant velocities, then even if you do the vector addition, it will lead to a constant value only, right? You can check it yourself also, right? And that is the most crazy idea, that any inertial frame of reference, if there is a frame of reference which is inertial with respect to one inertial frame of reference, then it will be inertial with respect to all other inertial frames of reference. And this is actually another way of saying that laws of physics will be same for all inertial frames of references, right? So this is an introductory lecture of special theory of relativity. This was the first lecture, and in this we have discussed about Gaussian transformations, invariance of Newton's laws of motion in under Gaussian transformation, right? Now in the next lecture we will be discussing about Lorentz transformations and all, and time dilation, those things. Okay, so this was the first lecture, and I hope so that you enjoyed this video. If you did, then please do like, share, subscribe, and please support this video. Bye bye, take care.